All right, so now we can do another case, but before we do that, uh, let's actually do this for real. Here's the IPython. Let's take a nice new environment. Let's go to PageRank 2. We don't need to change any parameters. We just copy it, and then we run it. And this one doesn't produce any pretty pictures. It just produces some numbers. So if we look at this, as we'll see, it does several methods. The method I went through is actually probably usually the best method, and this actually also the simplest method. And you feed in the array. This is the array which I called A. Here's the array I just went through. I'm just about to go to an 8x8 array called ops, and I now need to run it, having typed it in. And it comes back immediately. And we run these 5 methods, and they give nice page ranks. And if you look in detail, part of the font size too small here. But you will find that all 5 methods give exactly the same answer. It also tells you when it stops. And the first matrix needed just 18 iterations, and the second matrix actually needs more iterations, 87. And in fact, it doesn't quite give numerically the same answers, but differs in a very small decimal place. So that's running the code. You just get the printout and verify that the page rank. I mean, this is the rank of site 1, site 2, site 3, 4, 5, 6, site 1, 2, 3, 4, 5, 6, 7, 8 for the next matrix. So that's the PageRank Python here. And this is the second 8x8 matrix, which you got from a AMS website. I don't quite remember why, but they did not want any damping in this case here. We just, I typed in this, they have this on the website. I typed it into the Python code as a preset definition, and then we ran it, and we got this result, which these are the page ranks, and actually site 8 is much the largest page rank, 0.295. Next is site 6.2025, 7.18, and the smallest is site 3. And you can actually see here's this graph, and this is a version of the graph with coloring. So the lighter color means you're loved more, and then your page rank is higher. And page 8 is the lightest color, and poor old page 3, that looks like one of my pages, it has a very dark color because it's very sad as it was not liked by many people. Page rank of 0.03. 0.03 is probably very good in the real world, but if you only have a world with 8 sites, it's not so good. And you can see why it's not very good. It's only actually pointed to by one site, number 1, and number 1 is itself only pointed to by one site. So these poor old sites here, 3 and 1, just don't have much chance. Not enough people know about them. Whereas site 8 here, you see, has lots of people pointing to it, 7, 5, and 6. There are 3 other methods given on this website, and are listed in that PageRank 2 file. I'll just briefly mention them. The method we just went through, called the power method base, is just taking this equation here, x equals the damping factor, d times a plus 1 minus d times the matrix of ones, and times S is the matrix of ones. That's the method we already went through. Very simple to implement. Now, actually, you can slightly change the method, because if you do some arithmetic, you will find that S2 times X is just actually summing up the components of X. They actually don't matter what X is. They're always the same, because the components of X always add up to 1. So you can actually replace this by a slightly different form. X equals D times A times X plus 1 minus D times a fixed vector S1, where S1 is always ones. So that just gives you a refinement of the method, which is what's called PAR method. And remember, this method solved automatically in the Python code, and we print out the answer, and all methods give the same answer. There are actually 4 methods in the original Python page. I added one more method, which was called PAR method base 1, which basically I already described. It replaces the stopping criterion by a threshold rather than by a number of iterations. So we've gone through 2 of the 4 methods on the PageRank 2.py page. The last 2 are really mathematical curiosities and not such serious methods. If we look at the basic equation, x equals d times ax plus 1 minus d times s1, which was the form we introduced in the last page, we can write that as a sort of solver form. 1 minus d, a matrix, times x equals 1 minus d times s1. So this is a basic linear equation solver, and you can just, except for the special case d equals 1, where you don't get a good answer here, because you get 0 and you can't, in general, solve an answer with 0 there. You can solve these linear, that's because this is sort of the wrong way to think about it. So you can then call the linear equation solver and just get the answer. So this is not, in my opinion, a serious method for a real problem. It's mathematically correct, but highly inefficient, especially because the matrix A is sparse. This course doesn't really go through the different key ideas in solving in solvers, but when you have sparse matrices, you tend to use iterative methods, because if you use non-iterative methods, they tend to wipe out the sparseness and not exploit the sparseness, and that gives you wastes a lot of time, especially as this matrix is 25 billion by 25 billion on any row and column, only around 20 values are non-zero. So this is a hugely sparse matrix, not exploited by this method. So that's the linear equation method. It gives the right answers for this test cases we did, which these general comments are irrelevant for. And so it's fine. It is mathematically correct. Then we note that actually this, we can go back to the original form of the equation. X equals d times a plus 1 minus ds2 times x. So that's actually an eigenvector equation, and where x is an eigenvalue. And actually, you can show the eigenvalue is 1, and also that this is the largest eigenvalue. So actually, another way of solving this problem is to find all the eigenvalues and eigenvectors. And that's the last method, maximal eigenvector. That's a very general method, but in fact, if you only want to find one eigenvector, the maximum, then the PAR method, which is the first method, or the first 2 methods done already on the previous pages, it's much the most efficient. There is a refined version of that called Arnoldi's method, which is actually what you would use probably in practice, but you would not, the eigenvector is mathematically correct and the general solution, but you obviously need to exploit these key features. You only need one eigenvector and the one eigenvalue, and you need to exploit sparseness. That requires a certain solution method, which is effectively a sparse matrix vector multiplication. So that's the end of these 2 methods.